I welcome all viewers from Webex platform and PRL YouTube channel to the 31st Vyakhyaan in the PRL Ka Amrit Vyakhyaan series. This series of 75 Vyakhyans began on 4th August this year and is being organized every Wednesday 4 p.m. to celebrate the Platinum Jubilee of the foundation of PRL. The Vyakhyans are delivered by eminent speakers from India and abroad from diverse fields of science, engineering, art, and literature. Today, we are honored to have very distinguished speaker for the Amrit Vyakhyaan, Dr. Annapurna Subramaniam, Director IIA Bangalore. On behalf of the Director PRL, my colleagues, and also on behalf of Amrut Vyakhyaan Committee PRL, I extend a very warm welcome to Dr. Annapurni. With this, I would like to invite Dr. Nandita Srivastav to kindly introduce our speaker formally. Over to you, Dr. Nandita.
Thank you, Dr. Kuljit. It is indeed my pleasure to introduce Professor Annapurni Subramaniam, the Director of the Indian Institute of Astrophysics, Bangalore. A world-renowned scientist, she has almost 3 decades of research experience in stellar astronomy in topics ranging from star clusters, classical BE stars, young stellar objects, blue straggler stars, to Magellanic clouds, nearby galaxies, and UV astronomy. She has published about 150 publications and has guided 10 PhD students in this field of research. Professor Annapurni was the calibration scientist for the UV imaging telescope on board India's first and very successful space observatory, AstroSat. She has also led the Indian team of the observatory software in the international consortium of the 30-meter telescope, that is TMT, and successfully delivered the common software in 2019 for this project. She continues to play an important role in this project as the director of the IIA, which is the lead institute from India. Professor Annapurni is also the principal investigator of the proposed next generation UV-optical space telescope, named as the Indian Spectroscopic Imaging Space Telescope, or INSIST for short, leveraging on the experience gained from AstroSat and UVIT. Currently, Professor Annapurni Subramaniam is the chief editor of the Journal of Astrophysics and Astronomy, jointly published by the Indian Academy of Sciences and Astronomical Society of India. She is also a scientific editor of Research in Astronomy and Astrophysics, published by the Chinese Academy of Sciences. She also holds the chair of the membership committee of the International Astronomical Union. Professor Annapurni has received numerous awards and recognitions. To name a few, she is a fellow of the Indian Academy of Sciences, fellow of the National Academy of Sciences, life member of International Astronomical Union and Astronomical Society of India, Kavli Frontiers of Science Alumni, instituted by the Kavli Foundation and National Academy of Sciences, US. She is a recipient of C.V. Raman Young Scientist Award for Physical Sciences from the Karnataka government for the year 2018. She is also a recipient of the Sir Power Fellowship and Nasibuti Foundation Lecture Award, both in 2021. Professor Annapurni is deeply committed to the outreach of astronomy to students and general public. Besides pursuing her academic interests, she also follows her passion in music. As some of you may know, that she is a trained Carnatic musician and is a professional violinist. This afternoon, she is going to talk to us about ultraviolet imaging telescope and beyond. With these words, I now invite Professor Annapurni Subramaniam to deliver the Amrit Vyakhyaan. Over to you, Professor Subramaniam.
Thank you so much, Professor Nandita Srivastava, and thank you so much, PRL, the organizing team and Director PRL, for inviting me to talk to you, deliver a talk as part of this PRL Amrit Vyakhyaan program. And I'm happy to be here, and I will talk about the ultraviolet imaging telescope and the plans to move forward with the experience we have gained through that particular mission. So can I share my screen and
yes, please
start? Yeah, okay. Is it full screen now? I'm audible, right?
Yes, yes.
Okay, so I'll start with this thing. So basically, I wanted to set the stage by saying that astronomy started basically from ground-based astronomy, and use of telescopes started with Galileo in 1609. And with the birth of ground-based telescopes, we were able to look at the sky and also focus on particular objects and understand the physics behind the emission mechanisms, etc. So the current understanding of the way of our universe is ground-based telescopes has got a major contribution to do it. We have a lot of them on the ground now, and it continues to provide new knowledge every day. I have shown a picture of the sky of the Hanle sky, where we have an observatory, and Hanle holds one of the dark skies and ideal place to put telescopes because of sensitivity as well as good sky conditions, clear skies, and also dry atmosphere, so you can observe them in the infrared as well. So this is the 2-meter Himalayan Chandra telescope, which has been operated by IAA for the last 2 decades or so. So the bottom line is ground-based telescopes have long been the workhorses of astronomical research. Now, why do we need space telescopes? This couple of initial slides are introduction just to set the stage, and for those people who are not very familiar with it. So the space telescopes are needed because of 2 reasons. One, the wavefront which arrives on the telescope are distorted due to the presence of the atmosphere. The atmosphere does 2 things. Apart from the wavefront distortions, it also dims the light, and also it scatters scattering happens, and intensity reduces, and also lambda dependence in the scattering. So every time you take observations, you have to correct for the atmosphere which is present above the telescope. And the image conditions get deteriorated depending upon the condition of the sky. If we have a turbulent sky, a turbulent atmosphere, then the wavefront gets distorted quite a bit, and the wavefront which is arriving is distorted and results in the photons spreading over a large area in the detector, and the spread will actually reduce the detection limit. So the seeing, what the astronomers call it, make it an important parameter to characterize for setting up of observatories. So that is one thing. Second, the atmosphere does not let all the lambda to pass through it. And that is one of the reasons why the life on Earth has been surviving. So you don't have high energy emissions or gamma rays, X-rays, ultraviolet, etc. Arriving on the surface of the Earth because they are blocked by the upper atmosphere. But the cosmic sources do emit in these wavelengths, and if one wants to study them, then you have to put your detector above this atmosphere. And that is when the space telescopes start playing a key role. So just because we do not get them on the ground does not mean things don't emit. So you have to collect them and then understand the emission mechanisms and the physics which are operating in these objects. So space telescopes play a major role in the high energy emissions, but also in the longer wavelengths. You can see patches where the absorption is quite high, where you need information in certain part of the infrared bands from outside the atmosphere as well. When you go to radio wavelengths, it's completely clear, and you do get the signals without any problem. So if in the modern day astronomy, previously you could do just one wavelength and study how the object is in that particular wavelength. But that era is gone. The modern astronomy looks at combining the emissions or the energy or the flux emitted, energetics and across the wavelength to understand the physics which is going on in the object. So in order to do that, you need to have a combination of space and ground-based telescopes to cover the entire electromagnetic spectrum to get a better understanding of the objects in the universe. Now, what has been done in the field of space telescopes? How do I minimize it? Okay. Is this blocking the slide? No, right? The slide is fully seen, right?
Yes.
Okay, all right. So the Great Observatories program led to the creation of 4 big and powerful space-based astronomical telescopes, including the Spitzer Space Telescope, Hubble Space Telescopes, etc., over the period of 3 decades, starting from 1990. So these are the 4 ones: the Gamma Ray Observatory, the X-ray Chandra Observatory, the HST, and the Spitzer Telescope. Now, these have given the view of the sky in different wavelengths. For instance, you can see this, the Kepler supernova remnant is shown in 3 different bands, and the picture you see is different. The picture is color is different, but that is one. That is basically the it's an artificial color you add to it, right? What you have to concentrate is focuses on the distribution of the flux or distribution of the intensity, and that changes from wavelength to wavelength because the emission mechanism is different. And this has given us better understanding of what these objects are, or different, for that matter, large number of objects are. All said and done, space-based telescopes are expensive to build and also difficult to maintain and operate. So that is a different ball game other than the ground telescopes, where you can always maintain it, or remove and replace objects which are gone bad, or replace an instrument, etc. We've been able to service the HST, and HST has been able to produce excellent images and data for the last 3 decades or so. So though all the 4 telescopes have contributed to the understanding of the universe and looking back in time and depth, etc., Hubble has been had the largest public and media impact, along with its Hubble Deep Field observations, which has given rise to an important understanding of how the gaps in the sky actually look like. Moving forward, what is the status? I don't think I need to introduce JWST to you, but then just for as a filler, we saw the launch of JWST in December 2021, and it is basically the next generation telescope to the Hubble. But I should also mention that though it is supposedly the next generation for Hubble, it'll operate in the infrared only, and the capabilities in the visible and ultraviolet will not be there in the JWST. But in the infrared, it'll exceed the previous performances of in all the observatories out there. And JWST also makes the next step towards the segmented telescope in space. So ground-based telescopes saw a major shift in the late 90s. We had only one mirror telescope for the nighttime observations. Now, with the Keck, etc., we moved to segmented mirror telescopes, and that is the future to go, because you cannot build monolithic one single mirror as a primary mirror, more than 8-meter class telescope. So you need to go into segmented mirror. So that is done on the ground, we know it. But then putting a segmented mirror in the space is a very tricky operation, and that is what JWST has achieved. It's indeed a major milestone. So JWST has different cameras and spectrograph, and this is the overall layout schematic, and it has got a camera, near-infrared spectrograph, near-infrared, mid-infrared instrument, and the fine garden sensor, etc. And this is produced by different collaborations, and these kind of large space telescopes require multiple collaboration with multiple agencies, multiple organizations, and multiple groups cutting across different nations work together to produce and launch these kind of telescopes. Now, they also have, where do we launch? We launch these in either in the low Earth orbit, or in the sun synchronous orbit, or in the Lagrange points. So in early mission time, many of the satellites or payloads are put in the low Earth orbit, which is about 300 to 800 kilometers. So you can have a 90-minute orbit around the Earth, and AstroSat is at about 650 kilometers. And the other things are like the closer one is ISS, and HST has a slightly higher orbit, so they are in LEO. You also can have sun-synchronous orbit where you can actually go as a polar orbit, and then the heights are similar, like 600 to 800. And the proposed mission INSIST is we are proposing to have this orbit. The reason being, you get a larger coverage of the night sky. For per cycle, the amount of night sky you can have is very limited in this kind of an equatorial orbit. But in the low Earth but sun-synchronous orbit, you'll get more number of hours for the night sky. So that is the difference here. Apart from that, these are closer. The faraway ones are the Lagrange points. So this is the sun and the earth system where you can have the points where the gravity is balanced here. And around that fictitious point, you can have an orbit, and the satellite or the payload placed in this orbit can stay there and constantly either see the sun or not see the sun. So if you consider L2 where JWST is going to be, then it is behind the Earth. So the Earth blocks the sun, so you get a clear view of this night sky, and it is constant. When the Earth goes around, it is always be on the other side. So continuous observation can be performed, but it is 1.5 million kilometers from Earth. So towards the sun is L1, and that is where the Aditya L1 mission is going to be. And that mission helps, the position helps it to see the sun most of the time, all the time. When the Earth moves around, it will always be in between the Earth and the sun. So it can see the sun with an unobstructed view. So these are the major locations where we send space missions to. Now, the space missions, success of the space missions are on two things. One is, of course, getting the instrument ready, calibrated, as well as launch it to make sure that it is already launched properly and just reach there without any problem. And after doing that, you collect the data, and the pipeline processing, all that are equally important to derive science-ready images, and then one start doing the science data. But over and above this, you also need to have data archives, dissemination system, along with tools and techniques which are readily available. So for a larger community participation, and also using data beyond what was actually proposed as part of the mission, because the scenes do evolve, the landscape does change, and one would like to go back and take a look at the data in a new perspective. The data should be made available through archives. One such archive, which is very popular and very well used, is the Mikulski archive for space telescopes. You also have the HISARC at NASA's HISARC for High Energy Astrophysics Science Archives and Research Center. They not only give mission-specific data, mission-specific tools, etc., so that people can start working on it. This is a big thing in astronomy, and particularly for space sciences, where you do get a lot of data which are archived, and it is very important to house the tools as well. And COSPAR like organizations also carry out training sessions, because you have data, you have tools, there will be a lot of students and young researchers wanting to use them. So how to use them, you need to have training sessions as well. So it's everything put together over a larger period of time makes the mission and the investment quite successful. And you also reach to larger community in the whatever area of research it is being proposed for. And these archives also help to combine data across large wavelength. So you are looking at a particular object and wanting to study the physical mechanisms, and it also helps you to search and accumulate data across the wavelength so that you can study them in detail. So these are the general background with which the current scene is, like current international scene is this way in the case of nighttime astronomy. Now, science cases needing high sensitivity, you need astronomy from space are driven by these things. Science cases needing high sensitivity. So ground cannot produce that high sensitivity. So one very good example is the deep field. Hubble deep field has shown that nothing is empty, right? Because you have galaxies there. We thought was empty from the ground. So such sensitivity you cannot get from ground. Astrometric estimations, that is something which we have got Astrometric estimations would mean positional information and the rate at which the things are moving in the plane of the sky. You can, the space velocity, space motions are 3D. So you can deconvolve them into the motion across the sky and along the line of sight. Along the line of sight, you get it from radial velocity, but motion on the plane of the sky, it is a very, very small angle. That is angle per year you measure, and that angle can be converted to linear velocity, rather linear scales by once you know the distance. So these position and space velocity measurements are very difficult from ground, and because accuracies what you can get is not very good. So Hipparcos and currently Gaia missions have proved that space astronomy from space is very important. High energy observations, Chandra, Fermi, etc. Because as I already mentioned, multi-wavelength studies and transient studies where you need simultaneous observations. That is the point where AstroSat steps in extremely importantly, because that was precisely the reason why we needed instruments starting from very high energy up to visual, looking at the same part of the sky, same object, you can actually look at them simultaneously. And you can see that some missions can cover such a large range, but not many of them. So AstroSat is a multi-wavelength observatory where you can simultaneously study the activity or the physical phenomena of the object. So you can get the data simultaneously across the wavelength. So you can do a multi-wavelength study. But the point is that all the instruments on that particular payload should have a similar sensitivity so that you can gather for a large number of objects. So all the above address specific science cases related to understanding various objects in the universe. So in many science cases, science output are maximized by combining data from ground and space. So even in the case of AstroSat, we would, many proposals or many proposers have used coordinated observations with others, or combining where you do not need a simultaneous observations. You combine the data from other missions from space as well as from ground to derive maximum results regarding whatever science question one is addressing. So this is an example of that. This is taken from the paper, which is an AstroSat paper by Tripathi and Devangan. It is published just a couple of months ago. So this is like Aegean flaring, and so all kinds of things require simultaneous observation. This is on the best fit UV X-ray models for the 2018-19 June and the August and 2015 November using XMM Newton and AstroSat data. So combining the whole object is changing as well as the spectrum is also changing. So this is one a very typical example. So in this talk, I present some of the science results using the space data, particularly the UVIT, and combining with something else. I do not work on the transients. I work on things which are not that, I mean, they don't change too fast. So I can combine data which are taken earlier. So I touch upon some of the science cases which I have been involved with UVIT. So as giving an example, the WAD1 probes with ultraviolet is, you can see here, a galaxy would look like differently in different wavelength. The reason being the physics of emission you're probing is different. So you would be probing something much cooler in radio, infrared is slightly warmer, and optical is kind of hot, and ultraviolet is quite hot, and X-ray is really hot. So UV images of galaxies would actually be tracing the young stars, O and B stars. So you could actually, and the rest of the stars are too cool to be emitting in UV. So basically they become quite dim. And those which stand out will be the regions of star formation. So in general, if you look at the UV images of galaxies, you can actually see you can pinpoint and pick out the star forming regions. And in this era, you actually combine various wavelength data, because you know that the stars are forming here. Now the question, you cannot just say that, yes, these are the regions stars are forming, but that doesn't say anything. You just picked up some locations. But the science question you need to answer, why the stars are forming there? Why is the pattern, why is this spiral pattern? So you need to answer the science question. In order to do the science question, you need to know, is the gas there? Where's the gas coming from? What is the composition of the gas? Is the gas molecular? Is the gas atomic? And how much is the, is there any fountain which is coming out of the young stars, H2 regions, etc.? So which the science question demands the usage of other data as well as what is important from theory. So you mix up everything. So simulations, data, survey, the data can come from normal thing and surveys, etc. So you combine everything to throw light on the science question which you are proposing. So in this case, we were mostly interested in tracing star formation. You can see that the optical image of M83 galaxy, you can clearly see that this is a, sorry. You can see that the galaxy, the points are clearly visible as the star formation here, and the patterns kind of spread out, and there is a deformation on one part of the galaxy as well. So far UV emission, you can see from populations up to 100 million year. H alpha is only up to 10 million year, and you use models and combine everything to predict the star formation history in that particular region, and you use starburst spectra, etc. So this is one of the a study of the irregular galaxy where star formation doesn't have a pattern, and we also see that the emission, which is delineated by the purple here, has got some structures where the emission whole thing is determined by the presence of this circles. Circles are nothing but holes. So if you see this particular image, which is actually the H1 image, H1 does not have any H1 is missing in certain regions. And now why is H1 missing in certain regions? That's predicted as you have a supernova explosion or a large number of OB stars, which the stellar wind drives the entire gas in that particular region, small region. So it makes something called a bubble, or you can call it as a shell. So it clears the material. It can actually move the material into some shells. You can see this kind of drive the material into a shell, and that these shells have larger densities and they can collapse and form star formation. So the question that was being addressed is that, are the shells driving the star formation in smaller galaxies? If so, what is the fraction? Can you account for the shell driven, like the one generation of stars drive the star formation in the for the next generation? So we used several techniques using the H1 data, the far UV as well as H alpha, and mapping them and see how many can be triggered. Are there star formation where there is no shells or holes, so they're not triggered at all? So after a lot of analysis, this is just with the far UV data. The NUV data for this galaxy was not available, but deep data, we could actually see that not only about 50% was driven by this kind of a trigger, but rest of it, like you can see many of the outer regions where the star formation is still going on, is not triggered by the shells. So some fraction inside the galaxy, yes, there is a trigger, but outside there's no trigger by the shells. The other point which we could also understand was that the far UV emission coming only from star formation. So what is the critical threshold H1 density one should have for star formation? So that was also able to estimate as the 10⁻21 centimeter per square density is required for triggering star formation in any region. And this was also compared with other galaxies. Now, another area where we contributed is the understanding merged galaxies or recently merged galaxy. This is one such galaxy, NGC 7252. It's also called Atoms for Peace. This is, you can see this is a UVIT image, and this is a merged galaxy, and you can see this trail, the tidal tails of the merger. This merger has happened some time back. Now, the UVIT image was able to pick up the star forming regions in these trails. So these are the young star forming regions. We were able to quantify the ages of these star forming regions in the tidal tails. Now, the question is, you are creating small lumps of star forming regions. What will happen to them? They become clusters which are separated from the galaxy, or as tidal galaxies, or what is it? So one needs to estimate masses, one needs to estimate chemistry, etc. It was not possible from this data, but it is with a bigger telescope, bigger capability, it is able to do it. So even with a moderate UVIT, we were able to pick up the star formation in the tidal tails, which is actually quite impressive. The other point which was also known is that this galaxy has got a star formation in inner regions, but the UVIT image showed that the inner core is not actually having any star formation. It is lacking far UV emission. If you look at the HST image, it shows the very bright core. It holds an AGN. So though the star formation is suppressed in the center. So combining the UV, which is very critical to show that the presence of young stars, kind of indicated that the AGN could actually suppress star formation. So this is an indication, and these publications indicate the study of the tidal features as well as the letter paper on the AGN suppressing star formation. Moving to another one, we studied a lot of star clusters. And I must also point out the space can give parallax and prop motion, as I mentioned earlier. These space velocities are important for us to understand the kinematics of stars and also stars in nearby galaxies. So combining kinematics and combining the multi-wavelength observations, one can study the formation and evolution of normal stars as well as peculiar stars and clusters. So this was done using the UVIT image, and we produced a catalog of about 6 clusters. But we need membership, because once you're talking about special, like this you can see is the prop motion diagram. Let me come to this diagram first. This is the spatial plot of RA and DEC, which everybody knows. And we know that there's a cluster sitting there. Now the problem is, we do not know whether the cluster is, how many members are there for this cluster. If you put directly on the color-mentioned diagram, you can see a lot of contamination here. Now, which is the member, which is not the member, we do not know. But if we put them on the prop motion plot, you can see that actually the prop motion stars have, the field stars are in one, and then the cluster stars have a kind of a distribution, which you can model using a Gaussian distribution. It's called a Gaussian mixture model, and then separate it out and find the members. And then once you have the membership probability, you can use any data to find out what is the kind of emission mechanism. So we were particularly interested in stars which are like blue stragglers, which are out here. The problem is this is not a normal location for a single star evolution. If you do not know the membership, then you cannot say conclusively whether the star belongs to the cluster or not. So in order to overcome that difficulty, we used Gaia data and used a machine learning tool to combine the space velocity information and the emission information to study the peculiar stars. This study has contributed to the understanding of different types of stars. So we use this technique called the spectral energy distribution. This is nothing but the spectra overlaid here. But if you want to go and observe the spectra of a million stars, it is not easy. It requires a lot of telescope time, a lot of data collection, etc. But you can actually, if you can sample the spectrum at 10 different points, just like the dots shown here, then you can actually overlay and make a chi-square minimization to find out which is the best fitting spectrum. This is nothing but photometry, and these kind of colors show which are the filters which can use. So multi-mission data, multi-ground and space can be combined effectively to create this ACDs, and stars, by fitting them, you can actually see whether they are single or binary stars. So this is something which we have developed in the last 4-5 years. It is actually prompted by the UVIT data, because many stars we started getting excess in the ultraviolet, and it demanded modeling, detailed modeling. So what we are trying to do is the detection of white dwarfs, which are sitting as a binary companion to any of these stars in this particular diagram, HR diagram. One of the main things which me and my group have contributed extensively is the understanding of blue stragglers. So if I can take a minute to explain this HR diagram, that is the Hertzsprung-Russell diagram. Hertzsprung-Russell diagram has the luminosity on the y-axis and temperature on the x-axis. The observational counterpart is the magnitude, which is basically sampling the luminosity at a particular lambda, and the slope of the black body, which is a proxy to the temperature, which is on the x-axis. That's the color. So the ratio of the flux into lambda, that is B and V, which the magnitude becomes log. So it's actually a difference between the two. So in general, the clusters have a sequence of evolution, which is the main sequence, and then evolves to red giants, and they become white dwarfs. But you do see some stars which are actually forgotten to evolve. So they should have not been sitting here. They should have moved to this red giant branch as per the physics of stellar evolution. Now, why did they forget to evolve? How do they evade the stellar evolution? So the normal or the current understanding is that they actually gained mass after being born as a single star. They gain mass through perhaps a mass transfer process, which would mean they are in either binaries or in multiple systems. So for example, if these two stars are in binaries, what happens is if they come closer or one evolves and comes closer in the Roche lobe, then one star can transfer the mass to the other, where one becomes from the red, it becomes blue, in the sense that the red star can become blue. So it gains mass and become a more massive star, which will evolve much later, but the donor ends up as a white dwarf. So such a end product of a binary system can be sitting here. So how do you identify them? You can see these bright stars very easily, but then this white dwarf is not easily detectable. But you can detect the presence of white dwarf if you sample the spectrum in the ultraviolet. So this is shown here again. You have two binary systems. One is an accretor and one is a donor. The accretor is a fainter one. So the donor moves up here. The accretor moves up here because it has gained mass, and then it ends up as a white dwarf. So our studies of clusters have revealed the presence of these white dwarfs to many of these companions here. And we thought we will get white dwarfs and a kind of normal white dwarfs like helium or carbon white dwarfs, depending upon what evolutionary sequence it takes. Now, we actually were surprised to find that we studied many clusters over the last few years, and we ended up finding a large variety of them actually. So what it means is that when this donor, this binary pair is there, depending upon the mass of these companions, depending upon the orbital parameters of these companions, the star which accretes matter ends up as a blue straggler, but then the donor which ends up as a white dwarf can have a variety of end states depending upon when the mass transfer takes place. So in this diagram, you can see that our estimates of this combining data has helped us to find that you expect the stars to be within these dashed and dotted line, which are the white dwarf sequence. But what we are finding is that things are all over the place. So these are the results. I'm showing the combined results from all our studies, starting from, I think, a couple of more, 2016 onwards till 2022. So over these years, we have accumulated all these are all the counterparts, except the blue and red. These red are, so what we are finding is that the many of the companions are not actual white dwarfs. They are very low mass white dwarfs. So what is a low mass white dwarf? You let the star, which is the oldest as the universe, evolve, single star. So what will be the mass of the white dwarf it produces? It evolves and produces a white dwarf. And the white dwarf would be 0.45. So the universe is not old enough to produce a white dwarf which is smaller than 0.45. So that is the lower limit. It sets the lower limit. But if it detects something lower than that, that would mean that it is somebody took away its mass before it could evolve. So it's hasten its evolution. So such systems fall here. So we find many of them which actually confirms that these stars lost mass to something else. That is why it became lower mass. And the field, such stars are known in the field and they're shown here, which is in confirmation. So we think that we have analyzed only about 5 clusters. There's likely that the this particular area is full of these, and more clusters are needed to understand the demographics of what kind of end products one can get due to different types of binary evolution. And moving forward, we also have the globular cluster studies, which we carried out using a survey, globules. So though the globular cluster is like very rich and too dense, if you take the image in the far UV, since most of the stars are cooler, all of them become very dim, and you can actually resolve the core and pick out all the stars. So even though the UVIT has a very moderate resolution, because it's operating in the far UV, we are able to resolve the cores, and we have produced the first paper based on the globule survey of about 8 globular clusters, and we have added some few more to it. Is submitted, but the entire data has come and by a combination of we have previous papers with a few clusters that are all listed here, which also have contributed to the understanding of hot stars there. And just wanted to highlight the result here. So the previous such a galactic globular cluster survey was done by Galaxies. You can see this particular image here. So this is the hot stars in the cluster, and these are the other stars. One problem was that when this was done, the membership information was not available. Second, the Galaxy has 3 times worse spatial resolution, so they cannot resolve many stars. So the combined color diagram looks very confusing here. You can't separate out stars here. But a similar diagram for about 11 globular clusters is shown here. You can clearly see the difference. You can actually see sequences, and once you plot the isochrones, you can actually classify the sequences. These are blue stragglers, these are white dwarfs, a large number of them. These are hot horizontal branch stars. These are core helium burning stars, and these are the evolved from HB stars. They could be something like early AGB or all those kind of hot stars. And these are the variables. So this one clearly replaces the previous globular cluster survey from the Galaxies. And this is basically thanks to the resolution which is possible from UVIT. Now, so we have very good resolution, and the AstroSat, which is launched, is completed. Its lifetime of 5 years is over and is cruising to the completing the 7th year, and all the instruments out there are working, and we have wonderful data, and the publications from all these instruments are continuing to grow, when more and more data is coming in and more people are involved and more techniques are developed. Now, it is important that we have, this has given us a lot of confidence and given us a lot of training in order to how to do make a space observatory, launch it, operate it, and do science as well. So what is next is the question. So as a continuation, the Indian Spectroscopic and Imaging Space Telescope was proposed with in the 2nd year of its the UVIT operations. And this proposal was submitted as in response to the call for proposals from ISRO, and it was given some seed money. I'll come to that. The current so the question which we need to answer is that, do you need a UV optical telescope in the future? What is the international landscape like? Okay, just because we have gained experience in it does not mean it is relevant in the international scene in the coming decade. Now, you can see that the coming decade is going to see JWST is launched, Euclid and WFIRST, but they are all in the infrared. But if you want to look at the UV sky, so what is there in the optical? You have this Rubin Observatory and the LSST program going to give you large synoptic survey and deep optical images and transients and magnitudes of various objects will be going to come in by the end of next decade. They'll be flooded with it. Now, there is nothing out there in the UV. So it is actually an opportunity for India to put it forward. So I just give a nutshell of what has happened so far. The origin of the proposal is the first UVIT meeting in 2017. Then in response to the future astronomy calls, we submitted a proposal in 2018. And the proposal recommended by a review committee for seed funding in October 2018. The proposal moves on to the pre-project phase in 2019. Castor is in a mission which is proposed by the Canadian Space Agency, which has got similar characteristics. So we had a joint mission to see whether we can do we can combine these two missions together in September 2019. From then onwards, we've been talking together, and we put together Indian collaborators and teams, etc. We have been working on various critical elements to demonstrate, and that has been going on. And by this March, we'll be completing 3 years. And we think that we would move forward to the next phase of phase A for getting more into the finalization of the specifications, the optical layout, etc., etc., in combination with Castor. So it likely we are projecting it as a ISRO CSA combined joint mission kind of a thing. And the 6 big science questions which we started off with is driven by UVIT and the UVIT community. So imaging is driven by, it's a 1 meter class, so you can actually go deeper in space. But we also wanted spectroscopy capability, but with it'll be for the local volume. And so it'll be a combination. Operational philosophy was a combination of legacy surveys and a few down selected topics for large surveys and a guest investigator program. So to give you a overall specifications, we're looking at a 5-year mission of a 1 meter off-axis mirror with a spatial resolution is 0.2 arcsecond, which is extremely important because it's an excellent resolution when compared to UVIT of 1.5 arcseconds, and wavelength coverage. And we would like to have instruments for photometry, slitless spectroscopy, and multi-object spectrograph. Also for precision photometry for exoplanet science cases, and the rest of the things are shown here. And most of them, the top level objectives and requirements are in place. Details are still to be worked out. So one would have a array of mirrors where the reflection takes place. The heart of it is sitting in FSM because it's a fine steering mirror, which would actually correct for the jitter and drift and create images of that quality. And then you will have simultaneous imaging plane in a G band, a UV band, and U band, and also a field for multi-object spectroscopy. So if you find this complicated, you can actually focus here. So this is the imaging field in red, and that would be imaging simultaneously in UV, U, and G. You have an adjacent field, which is shown here in blue, which is basically the multi-object spectrograph. And the side G band is for putting a 1 star and getting the precision photometry. Now, details are there in science document, and a couple of papers are submitted. To give an example of the resolution, this is what is expected. This is the Galaxy resolution. This is the UV-80, and this is simulated INSIST resolution, which we expect. And field of view are something like this. And you could actually, in the case of UVIT, you can actually resolve the central region, and one should be able to pick up about a few hundred objects for individual spectroscopy. Just like in this case, you can actually take spectra of individual star forming regions in this particular galaxy, which is a small part of a galaxy actually. This field of view is similar to the field of view of the DMD, is similar to the HST field of view actually. How do we do the multi-object spectroscopy? It is through a digital micromirror device, and you can actually choose which mirrorlet. This is about 10 micron to flip, and these flip will be like this, and then you can actually get the spectra of the dispersion direction. So this is the kind of thing which we propose, and we are demonstrating it using a lab model, and the lab model is ready, and we expect to use it at 1.3 meter telescope in a few months to come. So the usage of DMD for multi-object spectroscopy is planned to be demonstrated in the ground itself. And sorry, I lost my cursor. Yeah, so these are the kind of science cases and science document. We are planning to put it together as a publication as well. So these are many science cases proposed, and the people involved are shown here. And these are the participating institutions as of now in the science cases. And PRL is, in fact, contributing quite a bit to it. And we have regular meetings, and Manas and Shashi join them. And Shashi, being the coordinator from PRL, let us know about the contributions as well as participation in science, etc. And when we move forward to the next phase, we would like to discuss and finalize as a team contributions from various national partners so that the roles and responsibilities are in place. So this particular thing, which was this during the seed funded project phase, we went through 4 reviews by a committee headed by Koteshwar Rao. And the last review, which happened a few months back, has recommended that this proposal is matured enough to go to the next phase. And we are working out the details to documents and all the work done during the seed funded phase, so that it can be recommended to go to the next phase. So that's all from me. Thank you. I look forward to have questions. I hope I didn't overshoot my time.
No, it's perfectly all right. Professor Annapurni, thank you very much for a very informative and insightful talk, highlighting the results of observations that were made by UVIT combined with multi-wavelength and multi-mission data, which has helped to answer several questions, scientific questions. And you've also nicely covered the future program for India with the INSIST project, and which sounds very exciting for Indian scientists. I'm sure there are several questions from the participants. And so I think we can now open the floor for question and answer session. And to conduct this session, I will invite my colleague, Dr. Manesh Samal. Over to you, Manesh.
Thank you, Professor Nandita. Thank you, Professor Annapurni, for giving a compact overview of UVIT and the results and what lies ahead as far as UV astronomy is concerned. So so I will try to take up questions from the members in the WebEx panel. Then we'll take up a couple of questions from the YouTube. So I request my WebEx colleagues to raise your hand so that we can take questions one by one. I see question from Mudit Srivastav. Mudit, please go ahead.
Hello, Professor Subramaniam. This is Mudit here.
Yeah, hi, Mudit. Yeah.
Yeah, hi. Very nice talk. Thank you very much for this. See, I have a question about the transient studies with INSIST. See,
Yeah.
in particular, the studies of the earlier phase of the transient.
Yeah.
You see, let's take the example of the AstroSat. If the transients happen right now, and if I go into the TO, target of opportunity modes, it takes in the fastest mode about couple of days before the observation commenced. So with the INSIST, if we take about its engineering capabilities as well as management aspects, how easy would it be to capture a transient, in particular its UV spectroscopy in its earliest phase within a day, within 10 hours, 5 hours? So that's my first question, and I'm having a second one also.
Okay, so I must admit that this mission is not driven. It's not a mission for transients. So the mission operation thing would be to large survey and cover the sky, and if possible do transients as well. As you rightly pointed out, if there is an important event which has happened, it is important that the mission is steered to capture the data from that particular object. So like the Swift UVOT mission, etc., are actually geared for only transient. So your primary objective is to make sure that your the scheduling aspects are also dynamic, that you actually can change it anytime. So currently with AstroSat, our scheduling is not so dynamic. You schedule the observations for a few days, and then you suddenly want something, the entire system has to be geared up so that the schedule can be made change and then upload the commands and do the operation. So there is some amount of delay happening. As you rightly said, it is not, it is it's not dynamic. It is kind of quite sluggish. But we have to build up that requirement right in the beginning, and also have an understanding of how much time and what is the policy in upsetting the entire schedule and changing the schedule and doing it, right? But if you have a transient telescope, then there is nothing, everything is dynamic. You have to set the uploading the thing every overnight kind of a thing, right? Because you will know what is up in the sky only in the previous day, or what is interesting in the sky. So we need to take a call on this and put required guidelines at the beginning itself.
Yeah, so thank you very much. So the related second question is, do you think another UV mission, maybe with a smaller diameter, 50 centimeter kinds of thing, which is specifically meant for transient so that it can immediately move to the transient within a couple of hours, maybe less than a day, would be a useful complement for the insist that at early stage when the transients is bright enough, you capture its spectroscopy with that smaller mission, and then later you write a proposal to insist for further follow-ups. So what's your thoughts on that?
Yeah, so that's an interesting thing. I think I have seen a couple of proposals from Israel on this, and also one more from Caltech on this. But we should also remember that the transients, when you have, you will not only be looking at UV, but all wavelengths.
Yeah.
So you also need to have other capabilities like X-ray and things like that. And then and it requires larger field of view. It also needs optical, because sometimes UV, there is no emission coming up and you need to identify the object, etc. So it is not really simple to have just a UV one there without an optical. So UV wide field and an optical may be good, but then I'm not the right person to say it because I don't work on transients. So I do not understand the requirements. But I think there are a couple of missions which require a larger, you don't need that much of spatial resolution. You can actually go with a couple of arc seconds. A few arc seconds is fine, but you need a larger coverage, because
Yeah,
the
mostly it
transient.
was to capture the UV spectra, because it is that area which has been empty since IUE, this International Ultraviolet Explorer, stopped. We don't have
Right,
any.
but then you should also remember that the spectroscopy requires larger aperture.
Yeah,
Photometry is easy. So there's a trade-off with too many things. So one has to think through the thing and do it. Yeah. It's a nice question, Mohit.
Yeah, thank you. I'm done. Thank you, Manas.
Thank you, Professor Annapurni. Next question, may I request Professor Ravindra Singh, please go ahead.
Yeah, thank you, Professor Subramaniam. A very illuminating seminar, Vyakhyaan. My question is related to the binary systems which you are mentioning. So there is a bigger binary system, and then there is a smaller one, and then there is a mass accretion going on. So one is the donor, another is the acceptor. So what happens that okay, in the standard scenario, if the mass of the star, of the dying star, is greater than 1.4 solar mass Chandrasekhar limit, the core of the star, the end of the product of the star, goes to a white dwarf. Now in this scenario, the mass is constantly being donated to the bigger star. So is it possible to have one possibility is have low mass white dwarfs? But is it possible, my question is it possible to have a failed white dwarf where a lot of mass is already secreted into the acceptor star? The donor star has less mass, and it could not develop the electron degeneracy pressure, and the star remains neither white dwarf nor the low mass white dwarf. Is it theoretical possibility? Is it also one of the possibility which is being pursued, or what are you meant on that?
Yeah, so I'm not looking at a possibility. What we are trying to do is to find out what kinds of, like you said, the donor at the end product, once the entire thing is given to the star, what it becomes is the question which is being asked. So you need short binaries for the mass transfer to start. Okay, so how low it can get? So let's say the two stars are non-interacting. They are on the main sequence. It can get interacting when the orbits come closer, or one of the star becomes bigger. Right. One of the star becomes bigger is because when it is evolving. and that becomes the donor, right? That is the one which transfers mass to the other star. Now, at this point, the core mass, which is the core helium, is about 0.2, 0.18 to 0.2. So in general, you don't get anything less than that. There may be something less than that. But the question you're asking is, are they degenerate?
Yes, yes. See, the entire cycle has to be repeated up to the carbon. So the final.
So pressure and the degeneracy sets in or not, we do not know. Such systems called the ELM, extremely low mass white dwarfs, are discovered only recently, and they also have a kind of atmosphere around them. So one way to look at the gravity is you need to find the gravity for, how dense they are. So you look at spectroscopic lines in the Lyman alpha and fit them and find the log G, which would tell you how dense they are in the core. But since they have an atmosphere, we do not know whether the core is degenerate as of now. I'm not sure. I do not know what is the status. But
then saying low mass white dwarf,
it
may be a misleading to some extent, because we don't know just a final state.
They are in the white dwarf region. So they are in the white dwarf region. But what is the structure of the core is what you're asking. So I am not sure about it.
Okay. Thank you.
Yeah. Next question I'll take up from Professor Swavati Goswami. Professor Goswami, you may go ahead.
Thank you, Annapurni. That was really insightful and, a thorough talk. I really enjoyed it. I have a simple question, which is you mentioned that AGN could suppress star formation.
Yeah.
So is there a simple way to understand that, why it is so? Or
yeah, so what happens is you need molecular clouds and large amount of material, gaseous material in the central region, which is actually the star formation would be going on because it's a merged product and you probably have more gas which is going in because of loss of angular momentum, etc. But if the AGN is triggered, then you can have energetic particles which can actually throw the material away or ionize the entire thing away. So two things, one, the jets could destroy it, or it can actually ionize the entire material around it. So the feedback, the negative feedback process from AGN was speculated, but not exactly observationally identified. So we have done it in a couple of cases where this is possible and AGN can actually suppress, but one has to actually do the detailed modeling to figure out what aspect of AGN actually has suppressed it. I don't know that.
okay, thank you. Thank you. It's very interesting.
Thanks.
Next question by Professor Sachindra Naik. Professor Naik, you may go ahead.
Yeah. Thank you very much, Annapurni, for a nice overview of results from AstroSat UVIT. Okay, my question is related to what Navindra has asked to some extent. Basically, the blue stragglers, those are in binary, right?
Yes.
And this mass of the blue straggler star is relatively more than the companion white dwarf, whatever you are suggesting, right? Am I right?
It's more than the turn of star, so that is how you are identifying that as a as a blue straggler.
Yeah. So then
blue straggler can be either single also, which I did not mention, because if these come too close, this system come too close, they can actually be merged and become one. Okay. So in which case you will still see a single star, but massive. Yeah.
But in case of binary, the companion is what is low mass white dwarf. That is what you suggested. So the mass of the companion white dwarf is less than the blue straggler star. Then the evolution time scale of this low mass star should be, I think, longer than the massive star of that is blue straggler. Then how come this companion less massive star became white dwarf and evolved faster than the massive star which became blue straggler? And that
just focus on this particular figure. So you have A and B, you have shown A and B here. A and B are here. And you can see my cursor, right?
Yeah.
So the A becomes, A is right here. It is near the turn off. So it becomes a red giant. It's evolving. Okay. Or somewhere near on this, it's becoming bigger. That's the point here. B is staying there only. But depending upon the orbit size, the A becomes bigger right here, increasing the size and starts transferring to mass to B. Now, what happens is depending upon the orbit, the mass transfer could be continuous or discrete. As in when it evolves, it could become more. So this particular star actually will have, if the mass transfer happens at the end of the red giant branch phase, then it'll actually kind of shorten its life and become a red giant, because it is you're basically exposing the core. You're removing the layers from outside and you're exposing the core. It is not taking the actual evolutionary time to go through this.
So
right?
what's the range of mass of these mass and age of these kind of stars, blue stragglers?
The blue stragglers age is depends on, I mean, it is as old as the cluster, but it can live longer because the additional, because let's say the star of a 1 solar mass would evolve off when the core mass becomes like 0.2 or something like that. But 1.4 solar mass will evolve only when the core mass becomes 0.3. So when you add mass to it, mass is on the envelope, right? So it can live more time on the main sequence.
Okay. Thank you very much.
So this is the what you're saying is that the star lower mass actually does not go through the actual evolutionary phase of the normal star. You are just exposing the core. So it will automatically jump from that to another location because of the property. It will not go through that particular evolutionary phase. I think that was the that is the answer.
Yeah. Okay. Thank you very much.
Professor Annapurni, I have a couple of questions. Like you showed very beautiful images of UVIT, in particular the globular clusters. My question is, the globular clusters are very dense systems.
Yeah.
So, I mean, of course, those UV bright stars might be visible in UVIT. Still, my question is whether you face some difficulty while measuring the fluxes of these stars due to crowding.
Yeah, it's very important, Manas. It's correct. Like for example, you can see 362. There are quite crowded. You can see M30. It is crowded. But on the other hand, 5897. It is not crowded. So depending upon the central density and the number of hot stars present in the central region, we will not be able to resolve the central cores because of the 1.5 arcsecond resolution. That is point number one. Second is that when we do the analysis of creating a diagram like this or like diagram like this, one has to make sure that you are not doing unresolved stars together, and these stars could actually be two stars together and bright because the flux is combined. That should not happen. So what we have done is we have this particular globules work and most of the work. The inner regions you can see here as HST.
Yes.
So the inner regions of the clusters we combine with the HST, I think that HUGS catalog data. Most of the clusters have HST observations. And the inner regions we combine with the HST data. And the outer regions, we have other problems because the UV bright objects could be a background quasar, which we have encountered. Because suddenly there will be a couple of bright objects. You would think that they are members, but they're actually not members. They're background objects. So one has to be careful. So for the outside, we combine with the Gaia data to find out the membership. So outside is Gaia data membership, inner is HST, and you have to cross match very carefully. Outside is the crowding is not much. You can see not much of overlap is there, but inner you may have two hot stars sitting very close by. We cross match with HST, and then only we take them, and those which are having overlaps or companions or within the two stars within that PSF, we ignore them. One has to be careful. You have to single-handedly pick them. We have some codes which can say that the centers are within some distance. We combine with, after cross-matching with HST, we see that and remove it, but we have to visually cross-match.
Yeah, I got it. I got it clearly. This combining HST and UVIT is the key to
it is the key. And HST for any star, you will have millions of HST stars. I mean, at least 10 HST stars there. But then the point is, you have to pick the evolutionary stage ones, because there will be a lot of main sequence stars which are unlikely to be bright in UV. So you have to classify them and take them. Yeah.
My next question is for INSIST, we are planning to have multi-object spectroscopy,
Yeah.
right? So that will be very, unique and key instrument as far as UV is concerned, as I can recall or remember. Okay.
Yeah.
So is it possible to go for around 20 to 30 stars in a single observations?
Yeah. So the field of view, you can see this is 1 arc minute here in the thing here. So what we are planning is about 2 to 3 arc minute.
Right.
2 by 3 arc minute. So 2 by 3 arc minute, you will be getting many stars. And if it is an AGN field like the central galactic nuclei, you can actually pinpoint things, and after you need a pre-imaging, and then you can pick out. So the sampling is of the order of 0.2 arc second to 0.4 arc second. So you will be able to sample the regions of that scale. And now with a 1 meter, which is actually the focal plane becomes very crowded, you cannot, it will be of the order of 10 micron. You have to have these mirrors to separate them out. So we are looking at a 1K by 1K mirror LED. Let me go to that. Yeah, here, 1K by 1K. So you should be able to get about, I think, couple of hundred of them, including some sky space for the calibration.
Yeah, fantastic. A couple of hundred, that means that would be really a great instrument for the future.
Yeah.
I see one question in the chat box from the YouTube. The question is by Manjari Raghunathan. And a question is, why satellite like AstroSat carrying multiple payloads are rare? Is there any specific reason for AstroSat to carry multi-length observation payloads?
It's an interesting question. It is like, the missions like Swift UVOT has multi-wavelength. Multi-wavelength missions are there, but then with the same characteristics, they are rare. So what we were looking at is we were looking at like AGN or the binary stars, like accreting binary stars, where they will be emitting in X-rays as well as in optical in the UV. So you combine all the data so that you can study simultaneously. So the missions, I think this particular mission was driven by the science requirement of the nation at that time. So the specifications would be based on what is the science question asked by the community, and based on that community requirement, you come up with the specifications, and those specifications become the instrument, the guidelines for making the instrument and the mission. So I think it's in that relation. I hope I answered this question.
Yeah, thank you. So I'll take another question by Mr. Vaibhav Dikshit, and he's asking, off-axis mirrors give a very good performance for on-axis sources, but perform very poorly for bigger off-axis fields, and also have very tight tolerance. The question is, how the effect of any miselement due to launch vibration would be mitigated?
Okay, I did not understand the first part of the statement quite clearly. So the system what we are proposing over here is an off-axis system, TMA design, and the design, also the alignments and all that would be tested, and also made sure that if there is any tightness in the alignment, or the it's a okay, I don't know whether the person is knowing all this, but all these things go through pre-launch vibration tests, thermovac tests, etc., to make sure that these even after all these tests, they stick to their performance, and they are designed to do that. All the engineering things require that these are taken care. Over and above which, after the launch, if there are any misalignment, we need to have plans to mitigate it. In the case of UVIT, there was no requirement, and it actually behaved very well. And the focus, there was no change in focus or anything. But in the case of INSIST, it is actually a very tight, very short focus. So the depth of focus is not very large. So we may need a tip tilt correction, one-time tip tilt correction for focus adjustment in the case of secondary. And the rest of it can also be taken care by the FSM. So fine steering mirror will also be there. So I hope I answered the question.
Yeah, thank you. Professor Annapurni has some time constraints, so we'll not able to take more questions, and she has mentioned that. So now I will request, Diksha Roy to give vote of thanks and conclude the section.
Thank you, Dr. Manis. On behalf of Director PRL का Amrut Vyakhyaan Committee and all PRL colleagues, I would like to thank Professor Annapurni Subramaniam for accepting the invitation and delivering the 31st Vyakhyaan of this PRL ka Amrut Vyakhyaan series. Thank you so much, ma'am, for such an excellent and insightful talk on UV imaging telescope, space telescopes, astronomy from space, and sharing your experience on working with UVIT. It was indeed very informative. Also, many thanks to Professor Subramaniam for interacting with audience and patiently answering all their questions. Next, I express sincere thanks to Director PRL, Professor Anil Bharadwaj, for his constant support and encouragement, Dean PRL, Professor D. Pallam Raju, Professor Nandita Srivastava, Chair, and Professor Lokesh Sahu, Co-Chair, PRL ka Amrut Vyakhyaan Committee, for successfully organizing the Vyakhyaan, and other committee members for their constant efforts. Thank you to all the audience members and viewers for actively participating in the session, both on YouTube and WebEx. We shall be back next week with another interesting Vyakhyaan. Till then, stay tuned and do follow us on Facebook and YouTube. With this, we have come to the end of today's session, and on this note, I would like to conclude today's session. Thank you all very much.
Thank you, Annapurni, for a very excellent talk.
Thank you so much.
It was quite informative for me also.